Welcome to This Explainer. I am so incredibly pumped you're joining us today because we're going to unravel a mystery that sits right at the very foundation of modern physics. We're taking something you probably thought was just, well, absolute, unquestionable scientific fact, and we're going to flip it totally upside down. Seriously, get ready, because by the end of this, the way you look up at the night sky might literally never be the same.
Okay, let's jump right into a very specific number. 299,792,458. This is it, the universally accepted speed of light in meters per second. And we are so intensely confident in this exact number that since 1983, the scientific community has actually used it to define how long a standard meter is. A meter is literally just the distance light travels in a vacuum in 1 over 299,792,458 of a second. No decimals, no wiggle room, it is absolute law.
But prepare to have that sense of absolute authority totally shattered, because the shocking premise of our explainer today is this: no one has actually measured light traveling at this exact speed in a single direction. I know, that sounds like pure clickbait, but it is 100% true. The speed of a photon traveling just from point A to point B, never been isolated, never been recorded. To figure out why, we kind of have to look at what scientists have actually been doing for the last century and a half, because every measurement ever taken has been of the two-way speed of light. It's like a giant cosmic bounce pass. It all started way back in 1849 with Hippolyte. He fired a beam of light through the gaps of a rapidly spinning gear, hitting a mirror about 8 kilometers away. By spinning that gear faster and faster, he found the exact speed where the returning light passed perfectly through the very next gap in the gear's teeth. And he calculated a speed that's remarkably close to what we use today. But here's the catch. Fizeau, and literally every single scientist since, has only ever successfully measured a round trip, a complete bounce back to the starting line.
So, think about what this actually means. The one-way speed of light has never been measured. Since we've only ever timed the round trip, light could theoretically be traveling at completely different speeds depending on which direction it's going, and we would have absolutely no idea. It could be flying incredibly fast in one direction and just slugging along on the way back. As long as the total round-trip time averages out to the constant we call c, the math still works.
Now you might be wondering, why not just use 2 clocks? The logical solution seems so simple, right? If you want to measure the speed of a baseball, you get a starting point, an end point, measure the distance, and use a clock to time the trip. So why not do that with light? Step 1. Put a clock right at your laser. Step 2. Put a second clock exactly 1 kilometer away at the finish line and set it to stop the exact moment it detects the laser. Step 3. Just look at the time difference. Sounds incredibly straightforward. But wait, hit pause for a second, because here is where we slam into a massive brick wall. Ask yourself this: how do you actually make sure those 2 clocks are perfectly synchronized? Because if they aren't ticking at the exact same identical millisecond, your speed calculation for that 1 kilometer sprint is going to be completely garbage. Welcome to the ultimate, inescapable logic loop at the heart of physics, the synchronization catch-22. Let's say you connect the 2 clocks with a long wire and shoot an electrical pulse from one to the other to sync them up. Well, that electrical pulse travels through the wire at, you guessed it, the speed of light. That means the pulse arrives at the second clock with a tiny time delay. You might be thinking, oh, no big deal, I'll just subtract the time delay. But how long is the delay? Well, it's exactly the one-way speed of light, the very thing you don't know and are trying to measure in the first place. You literally need the answer to find the answer.
I know, your brain is probably racing right now trying to find a clever workaround. Don't worry, you're not alone. Physicists have been trying to beat this for over 100 years. For instance, what if we just use a gigantic 186,000-mile fiber optic loop? Just shine a light in one end and see if it takes exactly 1 second to pop out the other side.
It's a super clever idea, but actually scratch that, we have to dismiss it. Sending light in circles just creates an average. The fiber loops around and around. If light travels slower when it's moving forward and faster when it's moving backward across that loop, it perfectly averages itself out. You're basically just doing thousands of mini round trips, completely masking any one-way asymmetry.
All right, let's try another one. What if we placed a synchronizing device precisely in the dead center between our 2 clocks, and we blast simultaneous pulses outward to sync them both at the exact same time? This is essentially how GPS satellites work, so surely this solves the whole shebang, right?
Nope, it doesn't. Even a multi-billion-dollar GPS network falls victim to the catch-22. Think about it. If light travels at different speeds depending on its direction, then the sinking pulse going to the left clock might arrive just a tiny bit faster than the sinking pulse going to the right clock. The clocks wouldn't actually be perfectly synced. One would be slightly ahead of the other. And it would be ahead by the exact, perfect mathematical amount required to ensure that when you finally use them to measure the one-way speed of light, you still just calculate the standard constant c. The system assumes light travels at the same speed in all directions to set the clocks, so the clocks are forced to only ever spit that exact same assumption back out at you.
Okay, let's try one last, desperate attempt. What if we completely bypass sending light signals to sync the clocks at all? What if we start with the clocks physically touching each other, sync them up manually right there, and then literally carry one of them really, really slowly over to the finish line?
Well, special relativity totally crashes that party. When you move a clock relative to a stationary observer, time dilation kicks in. The moving clock actually ticks slower. You might think, okay, I'll calculate the time dilation and account for it, or I'll just move it so incredibly slowly that it doesn't matter. But here is the kicker. If the speed of light depends on direction, then the standard formula for time dilation itself completely fails, because time dilation would also depend on direction. The very second you move that clock, you break the synchronization, and without already knowing the one-way speed of light, you have no way to calculate exactly how broken it is.
So, we are literally stuck. Let's fast forward, or rather rewind, to 1905 and see how the great Albert Einstein handled this impossible problem in his famous paper on the electrodynamics of moving bodies. His solution? It wasn't some brilliant, intricate experiment. He just realized there was no meaningful way to compare time across distances unless we established, by definition, that the time light takes to go from A to B equals the time it takes to go from B to A. Einstein literally italicized the words by definition to remind us of this profound truth. The idea that light travels at the exact same speed in all directions, it's just a convention. It's known as the Einstein synchronization convention. It is a stipulation made of our own free will, just so we can have a working definition of simultaneity. It's an assumption, folks, not an experimentally verified physical fact.
To put this into perspective and truly grasp the mind-bending implications here, let's compare two totally mathematically valid scenarios for chatting with an astronaut on Mars. In scenario A, the symmetric model, this is the one we all just assume is true. A message takes 10 minutes to reach Mars, and the reply takes 10 minutes to get back to Earth. 20 minutes total. Simple. But look at scenario B, the asymmetric model. Here, the one-way speed of light is half as fast heading toward Mars, taking a full 20 minutes to arrive. But on the return trip to Earth, light is instantaneous, taking literally 0 minutes. The total round trip is still exactly 20 minutes.
Let's walk through that crazy asymmetric timeline to see how perfectly it hides from us. Say at 12 p.m., Earth sends a synchronization message to Mars. Because light travels at half speed in this specific direction, it actually takes 20 minutes to get there. But the astronaut on Mars doesn't know that. He's relying on Einstein's convention, assuming a symmetric 10-minute trip. So when the message finally arrives, he sets his Mars clock to 12:10 p.m., completely totally unaware that his clock is wrong. He immediately fires back a reply, and because light is instantaneous in this return direction, it arrives on Earth at exactly 12:20 p.m. Earth time.
And boom, there is your staggering illusion of sync. On Earth, they sent a message at 12 and got a reply at 12:20. They think everything is perfectly symmetrical and normal, but in reality, their clocks are completely mismatched. Mars is reading 12:10, while Earth is reading 12:20. What they consider to be the exact same moment in time is a total illusion. And because of the catch-22 we just covered, they can never ever run an experiment to realize their clocks are exactly 10 minutes out of sync.
Okay, so what does this all mean for us? The takeaways are absolutely wild. First off, all of physics works perfectly, even if light speed varies wildly by direction, as long as that round trip averages out. Second, the one-way speed really could be half of c in one direction and instantaneous in the other, and we could never prove it wrong. And third, just think about what that means for astronomy. If light travels instantaneously towards us from the depths of space, it means when we look up at distant stars hundreds of light years away, we might not be looking into the distant past like we've always been told. We might actually be seeing them exactly as they are right this very instant. It's honestly wild to realize that something as fundamental as the speed of light holds secrets we literally cannot test right now. We choose symmetry because Occam's razor tells us it's the simplest explanation, but at the end of the day, it remains a choice. So I'm going to leave you with this final, totally perspective-altering question. If we can't definitively measure the one-way speed of light, and our clocks across the entire solar system might be living a mathematical lie, when is right now on Mars?